Good afternoon, everyone. This session will be chaired by Dr. Ramu Maddu. Ramu, you take over.
Yeah, hello everyone. Welcome back to BICPAMA NTU JSPS Joint Seminar. Thank you for joining us. This is Ramu from NTU Singapore. In this session, we will have to talk about spin-based data security and computing techniques. There will be 2 invited and 2 contributed talks with a short break between the invited and contributed talk. Our first speaker for this session is Professor Anupam Chattopadhyay from NTU. He will talk about data security. Professor Anupam, can you please go ahead with your talk?
Okay. Thank you, Ramu, for the introduction. Good afternoon, everyone. I'll just share my screen now. So can you all see the slides clearly?
Yes, we can see.
Okay, thank you. So it's nice to virtually meet all of you, and we hope in future we will get chance to meet in person and engage in more collaborative research. So thanks to Prem for organizing this workshop. And I will talk about hardware security primitives based on ARM, and this is my background. I'm working more on the computing architectures and electronic design automation and system level designs for security. So I hope we will find a common ground to interact with the people who are more from the technology and device sides. So a brief background and introduction why we are looking forward to the security primitives for emerging nanotechnologies is that there is a rapid advancement in the design of trusted systems. And for any kind of trusted system protocol, they are relying on some underlying security building blocks. And with the recently, there is an increasing emphasis on security services provided by hardware-based primitives, which is replacing resource-intensive and slower software-based security measures. And some key building blocks that I will discuss today are physically unclonable functions, true random number generation, and hash function. So the background is that most of the available protocols that we see now, or encryption techniques for device authentication, data transfer, are purely software measures. So this we use in our day-to-day operation for e-commerce or for digital signatures of sensitive data, and for sending across information through trusted security measures. And what's happening with the software-based measures is they are getting increasingly computational heavy. So one needs to look for even smaller, faster, and implementations with lower power and energy footprint, specifically considering IoT platforms. And this is the design side, and the other side, there is always an opportunity for determined attacker who can find secrets by looking into the information leakage in physical forms. So when the design is implemented in purely software-based measure, then it is sometimes very difficult to control the hardware-based information footprint that these protocols are leaving. So for that reason, the security and cryptographic researchers, they are looking forward to creating a trusted block that is as close to the device as possible. And that's where this research started happening. So there were some very interesting discoveries around 2000 called physically unclonable functions. And of course, true random number generations, so they were there for quite some time. But with the emergence of new non-CMOS technologies, so it became very interesting research topic to look into these devices and see whether we can build security at the bottommost level from the devices and circuits. So as you are all familiar with, so there are different storage technologies that emerged over last decades, like resistive random access memory, ferroelectric, FET, computing technology, then STT-MRAM, SOT-MRAM. In particular, in this in the project that we are running now with Prem, we are focusing on SOT-MRAM. And for this different emerging NVM device technologies, their storages and their computing capabilities, these are well studied. But from the security standpoint, it would be interesting for us to look into what kind of security services they can provide and how to build those circuits. So this is relatively an unexplored research area, although there are some works that are being done. So I will summarize the existing works and try to show the pros and cons of different approaches for building these systems. So of course, the first challenge is building any reliable and robust circuit system out of these emerging technologies is to first look into the data retention capability. If you want to maintain the same stored data over time, then the endurance, the number of times the program can erase or you can reprogram the device, specifically the NVM device, before failure occurs. So these are the design aspects. And there are some challenges that we face towards actually implementing this is random telegraph noise, which affects the rate current stability. And then the variation in the switching behavior, the device to device variation and the switching resistance. And although these are considered from the traditional design point, the random telegraph noise and the variability in the switching are considered as a drawback that they affect good design. But interestingly, these drawbacks are considered as advantageous when we try to build security primitives. So I will come to that shortly. So the first part, I will talk about true random number generation. So the goal of a true random number generator is to create a high entropy input, which actually acts as a seed for the deterministic CSPRNG. CSPRNG stands for cryptographically secure pseudo random number generator. So there are a lot of crypto algorithms that can produce pseudo random number. So the pseudo random number, we call it pseudo because in reality it's not random, but the cycle of this randomness after point of time where it starts repeating itself is so large that for all practical purposes you may consider it as random. So that's why it's cryptographically secure. So once we get the cryptographically secure random numbers or pseudo random numbers, we can use it for various applications. And for any digital system, you will find that there is a pseudo random number generator for wireless transmission, for automotive, like inside the in-vehicle bus system. So the pseudo random number generator acts as an important building block. Now the pseudo random number generator, they begin with a high entropy small seed input, and that's where the true random number generators or TRNG comes into picture. So TRNG does not begin from scratch. We have to start from the TRNG where we produce a value with high entropy that acts as the seed or the first step for the PRNG. So they often are put together that we have a TRNG followed by a PRNG. Now this is where the TRNG is where the uniqueness of the devices that comes into picture, and we will see how we can tap the entropy due to various variations or due to the random telegraph noise to build such TRNG structures. So there is a a protocol for modeling and quantifying whether a source of entropy is good or bad. And this is the typical NIST entropy source model for designing TRNGs. NIST stands for National Institute of Standards and Technology, which helps researchers to quantify and categorize various kinds of TRNGs. So in essence, the principle is like this. We start with an analog noise source, which is digitized. And in the ideal scenario, the digitization will lead to a random unbiased bit stream. But often this contains some minor biases which can be removed through a conditioning component. And whether this digitization is actually leading to a good random number stream or not, that can be tested through some health tests. So NIST has some randomness testing mechanisms that can be run dynamically or that can be run in several intervals. So once we see the quality of random number drops because the noise source is degrading or it is not good enough, then we have to stop considering the final output as a true random number. So this is the usual setup for random number construction. And at the very basic, the NIST test suite contains 15 statistical tests to study the entropy in the generated stream. Each stream computes a p-value that implies the associated closeness of randomness to null hypothesis, which should be ideally close to 1. Now, that's just the quality of the randomness, but as you can understand, for a digital system, it alone is not sufficient. And we have to look for other implementation parameters like the throughput, how fast we can generate the bit stream, what is the energy consumption during the random number generation, or you can have more composite metrics like throughput per area, energy efficiency over throughput, and so on. So these are different ways you can benchmark the quality of the TRNG. So for example, if someone is proposing a CMOS TRNG circuit based on thermal noise, then if you claim that an RRAM based TRNG or SOT MRAM based TRNG is better than that, then we have to show the improvement in some of the qualities. The first one, for the randomness, it must of course satisfy it. There is no way around it. It has to be a good entropy source. But the other ones like the throughput per area or energy consumption, these are relative metrics, and we aspire to do better in this if we are proposing a new TRNG. So when we looked into the different RRAM based TRNG proposals, and we actually limited ourselves to the studies and the research papers where they have actually tapped out. So it's not a simulation based. So in those studies, we have seen that primarily two different entropy sources are considered. One is the noise in the read current, and another is cycle to cycle variations in the switching. So within the switching variation, finally, there are further classifications based on set and reset speed, required number of pulses, and switching currents. So this is of course not comprehensive. And from the device or technology research point, if you look into from that perspective, I'm sure you can come up with many different entropy sources for the technology that you are looking into. So here are some examples that how people did it for, let's say, random telegraph noise. So this is the case where there are a number of read times and the current pulses that are followed with digitization. So if the alpha parameter is greater than beta, then we say the x value is 1. If it is less than beta, then x equal to 0. If it is same, then we simply hold. So the difference in the noise current is used as a source for generating random number, and this current difference distribution is shown to be sufficiently strong source of entropy. So the random bit stream is generated by digitizing the adjacent current values. So there are two ways to approach this general problem of identifying a good TRNG. Is either you can actually model the current source, and then you can say the properties of the current source is close to various random distributions or random functions. And that gives you a hunch or intuition that this could be potentially good entropy source. The next thing that you do is you actually build the circuit, and then you do the measurements, and you show that it passes the NIST randomness tests. So there is another construction that was published in 2017, where the TRNG is designed based on the switching delay time. So we have a diffusive memristor here, and there is a pulse, and this pulse is being propagated through the diffusive memristor when it is compared with a reference voltage. And there is a high frequency clock signal that is ending the comparator output and running a counter at the end. And this counter is something that is separate from the memristor circuit. So what we see from this construction is the series resistor voltage increases with the stochastic delay time, which affects the comparator's output pulse width. And based on that, when we are ending this with a high frequency clock signal, we can see that there is a variation in the switching delay, which is also found to be a very good source of entropy. So there is another one that is helping with the switching, the C2C pulse number variation. And in this case, there is a peripheral control circuit and there is a pulse generator, which is producing this 1-bit counters, and this is taken as an input to the D flop, where we also have the control circuit, which can turn on or off the D flip flop. This 1-bit counter is what is capturing the parity of the pulse number. So if you are generating pulses, then you can take it to be the even parity or odd parity. And at the end of the cycle, we sample the final state of the counter, and that is produced as one of the bits in the random number bit streams. So after studying this different type of TRNG constructions, we tried to get an understanding is what is the quality of the TRNG in terms of the implementations. So there are different TRNGs which are plotted in the y-axis here as the RM entropy, and these are different bit rates. So when we looked into the bit rates from the papers which is published these results, we saw that for the 1 by f to the power beta, this noise as a source of entropy, we have the highest bit rate. So similarly, we try to categorize this sources of entropy as per the jitter, metastability, MTJ switching, and RM entropy. And among this, the metastability is producing the highest bit rate. So which is a desirable property for TRNG, how fast you can produce the random number streams. On the other hand, if we look into the energy efficiency, that is the amount of energy that's consumed in order to produce one single TRNG bits. When we plotted this in picojoule per bit, then we saw that the RM entropy turns out to be the most energy efficient among the various RM TRNGs that are proposed. So here is a comparative chart for the evolutions. So if you look into the review paper that we recently published, and if you see the various papers that have actually tapped out and provided the design for the RM-based TRNG, there are not much. And surely this is a field that will become more and more, say, expanding over the coming years, because TRNG is an important building block that is supposed to be there in every digital system. So long as that you are providing an RM based or an NVM structure, then you can definitely exploit that NVM in order to gather some TRNG. So these are the different studies based on their entropy sources, the RM integration, what kind of switching material is used. And for some of them, you can see the bit rate is very high. For some of them, the energy efficiency is also very nice. They do pass all the NIST tests. For some, all the NIST tests are not passed. That means it's not a good quality entropy, and there needs to be further conditioning to remove the biases to produce the entropy. So these are the test conditions. And in some cases, this is the post-processing. So this is the post-processing. As I said, since it did not pass all the NIST randomness tests, it had to be further processed in order to remove the biases and make sure that the quality of random number is good. So this is about various TRNG structures. So in future for the TRNG, what we know is that it is not adequately present in conventional MOS technologies. And definitely the emerging non-volatile memory structures and ferroelectric FETs and this kind of computing technologies will be more energy efficient and faster compared to CMOS-based TRNGs. So TRNGs are quite resource hungry, but we try to limit the TRNG only for the production of the seed. And that's why they can start as a building block where the CSPRNG is cryptographically secure pseudo random number generator. They overtake TRNG after the seed level of production. But if the TRNG is shown to be quite efficient, then we can completely replace the CSPRNG and use only the TRNG. So of course, the future direction is to produce very high throughput and energy efficient structures. And there are also a lot of interest in 3D integration, which can be used to discover new entropy sources and new TRNG structures. And the health tests, whether it should be done per interval or statically or dynamically or on demand, how to integrate this in order to monitor its operation, it's currently largely unexplored. So if you look into these structures, so they are just a single TRNG circuit and that's it. But in practical deployment, the TRNG circuits are built in together with the dynamic health test, because due to some environmental degradation beyond the test condition, the quality of the entropy source can degrade and one needs to continuously monitor it. So the question is, how do we build a single system that has the entropy production, TRNG generation, and online or dynamic health test to monitor the quality of the randomness? So I move to the second part of the talk where we will discuss about physical unclonable function. Sometimes it's also called as a physical one-way function. This is a construction that is inspired by the one-way functions people knew about in cryptography. One-way functions in a simple sense is that if you give an input, you reach an output, but from the output, you can never go back to the input. So that's why it's called one-way function. And it's also considered as unclonable. That means if you don't know the exact circuit structure, then it will be impossible for you to replicate this in another form. And exact circuit structure from where the unclonability properties are derived are based on some manufacturing variations, which makes it very difficult for someone to actually recover all the intricacies of the circuit without destroying it. So that became a very important structure that people started using for fingerprinting devices. So in one sense, you can also consider the physical unclonable functions or PUFs as a device level fingerprint. In the same way that we all possess an unique and individual biometric that is impossible to clone, we can also build some unique fingerprint for each device during the manufacturing process itself. So this was first identified by Ravikant Pappu in 2001 as part of his thesis in MIT. And since then, people started adopting these ideas in different domains, and there are proposals for silicon physical unclonable functions. And this also has become, say, de facto building block of any digital system, because we want to prevent cloning. We want to prevent reverse engineering and IP piracy. We want to store the keys built in the device in an unique way. So all these properties are satisfied by physical unclonable functions. There are already CMOS physical unclonable functions. There are big corporations, companies which are just selling physical unclonable functions as their IP. So the way it works is that again, we build from a unique entropy source, and then there is an extraction circuit that creates a reliable and unique random bit string. Now, this unique and random bit string is something that we talked about in the TRNG. But in the physical unclonable function, there is a slight and subtle difference to this, is where we build the puff circuit, which is associated with a challenge and a response. So the challenge is a set of binary values, and its corresponding response is also a set of binary values. So if we go through the similar design and similar manufacturing process, then we get an unclonable response bit generation, which becomes property of the device. Now, in case of a TRNG, we are not sending any challenge. We are just telling generate random bit streams, and it is generating it. In case of physical unclonable functions, we are sending a challenge. One of the puff properties that it must satisfy is if I am giving the same challenge every time, it should give me the same response every time. But this challenge response pair, that is unique to one device or one puff. So that means there is a large device to device variation, which is again considered as a disadvantage if we are manufacturing devices in bulk. But for the puff construction, this is a benefit thing. It's advantageous because each device has their own unique fingerprint. So within the puff classes, we make distinctions between strong puff and weak puff and reconfigurable puff. In the strong puff, the CRP space is very large. That means depending on the number of challenge bits, we should have exponentially big table of CRP space. And the applications that is found is an authentication. So if someone wants to authenticate a device, then they can send a CRP challenge and they get a response. By looking into the response, which is validated with already pre-recorded responses in the database, one can verify if the device is original or if it is fabricated or it is a reverse engineered IP. So even if you reverse engineer the full circuit, the physical unclonable function cannot be reverse engineered. There is also a sense of weak puff, which is distinguished from the strong puff by the number of CRPs, that it is linearly dependent on the component subjected to the intrinsic variation. It is primarily used for preventing counterfeiting, tampering, and ensuring device integrity. So for weak puff, you can quickly check whether this device has been cloned or if it's original. But unlike strong puff, you cannot use this CRP data to create more complicated security protocols because the number of keys that are there in the CRP space is small. And sometimes you may want to repurpose a device for a different user. In that case, you go for a reconfigurable puff, where based on some particular inputs, one can completely override the existing CRP space of the puff. So now I try to explain some of the constructions of protocols for physical unclonable functions. So let's say I have an IoT system and I have an IoT device which needs to be authenticated from some server. So the IoT device can send its own identity and pre-stored value n to the server ID, which finds that ID in the memory, reads the CRP, and generates a particular value which is unique to the server, and then sends an encrypted data from the server to the IoT device. Now, when it is sending this particular value RS, then the IoT device, since it has its own implementation of the CRP space, it can verify the message authentication code or the MAC, and that it can send it back to the server ID by constructing its own MAC. So here it's important to note that the IoT device is physically implementing the puff circuit, whereas the server, which is like a trusted third-party server, it already has a pre-recorded database of the entire challenge response set. So when it is sending a particular challenge value, it can find a response, and using that response, it can generate the MAC, So when this response is sent, it knows the challenge. Corresponding to that challenge, it can create its own response and create the MAC. So when the IoT device is sending the MAC back, then the server can verify the MAC that it is same as the one it has recorded in the CRP database. So we say the authentication is successful. Now at the circuit level, what we have is we have some enrolled puff values, which also the server contains. And the IoT platform, or the mode, as we say, it is sending the puff as a key for encryption or decryption purposes. Because the puff, inside this puff, it is basically storing the keys that can be unique to this particular device. And here you can also note that this IoT device is holding an TRNG, which can directly use for the encryption purpose, or the encryption engine can contain a pseudo random number generation and perform the encryption. So from this, you can get an idea that though the TRNG and puff are key building blocks that are to be there in any crypto processing unit inside an IoT platform, or inside a server, or inside even mid-range devices like the smartphones and so on. So coming to the constructions of the physical unclonable functions, similar to the TRNG benchmarking, we need to satisfy certain properties when we claim this is a good puff. And there are 4 properties for a puff benchmarking. The first one is the uniqueness. That means each of the puff circuit from device to device, it should have its own unique response. So there can be inclination of different puffs to produce a similar response bit for a similar challenge, and how much it is overlapping, that can be discovered by the bit aliasing. Then there is a question of uniformity, that the puff should have equal number of zeros and ones in its response. Otherwise, it might be possible for an attacker to reverse engineer the whole CRP table, because it's essentially a part of the Boolean function. And if I am sending a challenge, I am getting a response. So after recording few challenges and responses, one can sense that this is a Boolean function like construction, and can create the complete table out of it. So in order to reduce that possibility, it should have good uniformity. And finally, the reliability. That means if I'm sending the same challenge, then it should give me the same response, no matter at what condition or at what environmental situation it is the circuit is being tested. So over time it can degrade, but this reliability has to be maintained. So here are some constructions for the RRM-based puff cells. And in contrast with TRNG, the puff constructions are always associated with a challenge response pair. So there are 2 constructions which were proposed as early as in 2014, where we look into the comparison between a data array with a reference array, or a data array with another selected cell. So this is a data cell with another selected cell, and data cell with a completely separate reference array. And when we are doing the selection, then the particular reference array or the particular bits that we are selecting can be put as our challenge bits. And the value that we are getting as the output will be considered as the response bit. And since the challenge bit is restricting us to a particular word line and bit line, we know that if I trigger this word line and bit line multiple times, it should give me the same response when compared with the reference array. So this is one of the early attempts for the bit generation. There is a full RRM array puff that was constructed, where the challenge string is a random voltage and pattern, where we can enable certain rows and columns, turning some RRM structures.
You are exceeding the time, so you have 2 more minutes to
Okay. So then we can look into the SNCC current path, and then the mux is selecting the current response, comparing with reference current, we get the response bit. So we have also plotted this CRP space. When the number of CRPs is very high, these are categorized as strong puff. So there is a full range of strong and weak puff that are designed using CMOS, and there are puffs with RRM belonging to this range. So when compared with different switching mechanisms, 0T, 1R, 1T, 1R, we figured out that the comparatively better energy efficiency is achieved if we look for the 0T, 1R, whereas the bit cell area, this is also lower for this. So in general, 0T, 1R is better suited for RM puff constructions. So this is a more detailed table that you can find also in the reference paper. And in future, so there is a lot of work to be done for the puff construction, like the reconfigurability is rarely studied so far. And the same array that is used for the RM device as memory can also serve as the puff structure. So this is not yet well studied. So we have only independent puff constructions, not that is overlapping between puff, TRNG, and memory. So it can serve all the purposes. And finally, for the hash functions, so I will just go directly to the hash construction. This has been studied only for one particular paper, and this is also a very important security construction and well suited for implementing in a crossbar memory, but it has not been studied well. So in this particular construction, they also leveraged on the SNCC path, where you can give a prefix, message, and suffix, goes through a scrambler, sends the address and value. From the crossbar, you do a differential read over the SNCC path, get back to the scrambler, and feed to the crossbar again. So with this loop, you multiple times, and you finally get a hash construction. Yeah, so that's more or less. I had to rush last part, but there are these three construction which people are studying in the emerging NVM structures, and a lot of interesting work still remains to be done. So we are studying some of the building blocks here. So thank you for your attention, and if you have any questions, I will be happy to answer.
Thanks for the nice talk. So now the talk is open for questions. So if you have any questions, please raise your hand. Then I have one question regarding the random number generator concept. So if I'm correct, like in one of your slides, you have shown that there are no CMOS compatible random number generators. But we are actually proposing some Spintronic based random number generators. So what is the thing that we don't have it in CMOS and we can attribute it in our Spintronic devices?
Okay, so it's actually completely open. So you can have good entropy sources also from CMOS as well for Spintronics. But the advantage that we see clearly with Spintronics that it can produce random number entropies with more energy efficiency and smaller cell area. So it's basically scaling down the technology.
Don't have explode, I mean to say.
So the security primitives like TRNG or PUF, these are relatively new construction that people are going deep down into the devices. 20 years back, people were not thinking of so much of CMOS TRNG because there were some circuit construction and you can get a seed very easily. So you put a small seed and the rest of the circuit will be cryptographically secure PRNG. So now people are finding that TRNG itself is quite energy efficient and it can serve all the purposes. So if I find a very good construction for the TRNG, I will rather skip the PRNG completely and just put the TRNG itself.
We still have time. So I have a small question regarding again random number generators. Like what are the current, because it's not still commercialized, so what are the current bottlenecks that needs to be addressed in order to make it into commercialized product?
So for the PUF, I know definitely it's commercialized. It's an SRAM based PUFs are already available in the market, and there are a lot of NVM PUF and TRNG structures that are proposed even with the prototype demonstrated. So if you can show it with a prototype, the quality of the random number or the PUF is good, then it can be definitely commercialized. So there are lots of patents actually. So I don't know any company which is just selling the TRNG, but TRNG builds forms an important IP for many companies. So you will find patents for almost all semiconductor companies. They have RM based TRNG and PUFs submitted as patents. And there are some companies which are actually selling quantum TRNGs. So that has gone to that level. So there is a company called ID Quantic that has commercialized quantum TRNGs. So the goal is always to find a more efficient, smaller, low power source of entropy. That's it.
Does anyone have any question? If not, then we close this talk. Then we can move on to the next talk. Thank you, sir.
Thank you.
So our next talk is from S. Fukami, Professor S. Fukami from Tohoku University. This talk will be on stochastic magnetic tunnel junction for probabilistic computing.
Okay. Thanks for introduction. And can you see my slide?
Yes, we can see this.
Okay. So can I start?
Yes,
can I start? Okay.
We can start. Yes.
Okay, so thank you for introductions. So first, I would like to thank the organizers, Prem and Professor Tanaka, Yoji Tanaka Sensei. So I'm very happy to have this opportunity to share with you our recent works. So the title of my talk is Stochastic Magnetic Tunnel Junctions for Probabilistic Computing. So my talk is very different from the previous work because I will talk about the computing, but there are several common parts, which is we also use the stochastic behavior of physical devices, and the technology I will present is for the computing, but it is also used for the for example true random number generators, and also I think it can be also used for the PAF application. Okay, so let me start my presentation. Before that, let me introduce our collaborators. So this work was mainly performed in the team of the Hideo Ono in Tohoku universities, and also the computing part done in a collaboration with Spirio Datta's groups in Purdue University. Okay, and this is the introduction of my, this is the outline of my talk. So I will first give a broad introduction to the general audience. And so I will give a brief introduction to the Spintronics for unconventional computing. And then I will describe what is the probabilistic computing. And after that, I will show a proof of concept demonstration of the probabilistic computing. So I will show a demonstration of the integer factorization using a stochastic magnetic tunnel junction device. And after that, I will show a device technologies, so which is necessary to scale up the probabilistic computers. So I will discuss how we can make the fluctuation of the stochastic MTJs faster. So I will talk about the nanosecond fluctuating stochastic magnetic tunnel junction device. And finally, I will summarize my talk. Okay, so let me start from the introductions. Okay, so first I will start from the representative functional spintronic devices, which is the magnetic tunnel junction device. So as I believe that most of you knows well, the magnetic tunnel junctions can store the information, can represent the information as the direction of the magnetization of the free layers, and the direction of the magnetization of the free layer can be switched by applying a current through these MTJs, and also the difference in the direction of the mutual direction between the of the magnetization between the free and reference layers, so parallel and anti-parallel, can be detected through the by the resistance through the TMR effect. And so this MTJ devices has several unique properties, including the non-volatilities and high-speed operation capabilities, and high endurance and scalability and low voltage operation capabilities, and also compatibility with the back-end of line process. So these properties are very promising to realize random access memory applications, and magneto-resistive random access memories has the commercialization of the magnetic random access memories has recently started using the spin transfer torque-induced magnetization switching. So as I mentioned, these properties are very promising to realize random access memories, but the Spintronic devices also had several unexplored functionalities, which includes analog memory functionalities or analog digital tunabilities, and short-term memory functionalities, nonlinearities, or stochasticities. And if you use these two properties simultaneously, we can expect a new paradigm of the computing, so the unconventional computing. And today I would like to concentrate on the stochasticity of the, I'd like to show a possibility to utilize the stochasticities for the unconventional computing. Okay, so before that, let me briefly summarize the unconventional demonstration of the unconventional computing with Spintronics demonstrated so far. Okay, so several years ago, we found that by using an anti-ferromagnetic structures, the magnetization or the resistance of the device can be controlled in an analog manner by changing the magnitude of the applied current, as shown here. And after that, we constructed demonstration systems of the artificial neural networks, and we showed Hopfield model-based associative memory operations using this analog spin orbit torque devices as an artificial synapse. And also we found that by just changing the device size, we can realize the analog and digital memories using the same material systems. And then we showed the characteristic dynamical functionalities of the synapse and the neurons using these devices. So we showed the spike timing dependent plasticities of the synapse and leaky integrate and fire properties of the neurons using these Spintronics devices. So these are also promising as building blocks for the spiking neural networks. And this is the work by different groups, so the European teams. So I believe that Johan presented yesterday about this work. So the short-term memory functionalities and the non-linearity of the oscillators can give us an opportunity to realize the reservoir computers. And 3 years ago, the Julie Glorier's teams demonstrated the reservoir computing, so the sound recognitions using spin torque oscillators. And last year, last year, the Johan's team demonstrated the same functionalities using spin Hall nano oscillators. And the main topic of my main topic of my talk today is the stochasticities. So by using the stochastic behavior of the Spintronic devices, we have a chance to realize the probabilistic computing, which is promising for optimizations of machine learning and invertible logic. Okay, so next I would like to talk about the computationally hard problems. So the a famous computationally hard problem is one of the famous problem is the traveling salesman problem, which is categorized into the optimization problems. So this is the map of the Tohoku regions, and the Tohoku University is located around here. And so there are several beautiful spots which I'd like you to recommend to visit. So the traveling salesman problem is that what's the shortest route to go around these spots and return to the origins? So this is a very typical computationally hard problems, and as the number of the spot increases, the conventional computers cannot efficiently solve the shortest route with a reasonable time and reasonable energies. Okay, and one more famous computationally hard problem is the integer factorizations. So as you know, the multiplication is a very task for today's computers, but the inverse process, integer factorization, is difficult for today's computers. And this difficulty forms the basis of today's data encryption technologies, as the previous speaker mentioned. So, okay. And for such computationally difficult problems or the complex problems existing in natures, Richard Feynman gave famous lectures in 1981. So entitled Simulating Physics with Computers. And in this lecture, he mentions that if you want to make a simulation of nature, you'd better make it quantum mechanical. So this is a famous suggestion for the possibility of the quantum computing. And this talk has triggered today's extensive effort to realize the quantum computers. And in addition to these suggestions, although this is not recognized well, he also gave another suggestions. So he mentions that the other way to simulate a probabilistic nature is by a computer, which itself is probabilistic. So this means that this suggests another computing paradigm with so-called probabilistic computing, which is similar but different from the quantum computing. So next, let me describe what is the probabilistic computing. Okay, so the fundamental principle of the probabilistic computing is this Boltzmann equation, the Boltzmann distributions. So this equation tells you that the lowest energy state is most frequently observed. And so this is the basic principle of the probabilistic computing. And by the way, this equation also tells you that the lowest energy state is observed by decreasing the temperatures. And this is the basis. This is the fundamental principle of the quantum or simulated annealing. Okay, so let me explain in more detail about the procedure of the probabilistic computing. So this shows the flow of the probabilistic computing. So first, you will have some problems which you need to solve. And then you need to first define an energy or cost function for the given problems. And after that, you map the cost function to a physical system with probabilistic nature or a physical system with stochastic neurons. And after that, you just watch the system and acquire statistics. And finally, you can obtain an answer as the most frequent state. So the most frequent state is approximated as the answers. Okay, so let me explain schematically. So first, so you have some problems, and then you need to define a cost function or energies for the problems. And then for the quantum or simulated annealing, you need to reduce the temperature, or you need to reduce the effective temperatures. And then at the beginning of the calculations, you have each state with almost equal probabilities, but by decreasing the temperatures, your system converges to one particular state, which corresponds to the lowest energy. So this corresponds to the answer of the given problems. And for the probabilistic computing, you also need to define cost function or energy at the beginning, as in the case of the quantum or simulated annealing. And then you just need to keep the temperature high enough and fluctuate the systems and take the statistics. Then, as the time goes by, you can obtain a distribution of the observed states, and so you can obtain the answers as the most frequent state, as shown here. So the one of the important point is that you can obtain the most possible answers, and the second and third, fourth possible answers, as shown here, by the one calculations. Okay, so with that, I would like to move, or I will move on to the next part and describe or present the proof of concept demonstration of the integer factorization using the Spintronic technologies. Okay, so the flow of the demonstration of the probabilistic computing is shown here. So first we need to construct the device which has the controllable stochasticities. And then you need to construct a bit which shows the sigmoidal response to the analog input. And after that, you need to construct a circuit which consists of the probabilistic bit which are connected with the synaptic weight logic. And after that, you need to define a cost function and map it to the probabilistic circuit. And we chose an integer factorization as an illustrative example of the optimization problems. Okay, so let me show one by one. Okay, so the first I will talk about the device technologies to realize the stochastic bit. Okay, so as I mentioned at the beginning, the magnetic tunnel junctions can realize non-volatile magnet-resistive random access memory technologies. And about 10 years ago, our teams found that by using a cobalt iron boron MgO-based magnetic tunnel junctions with perpendicular easy axis, you can simultaneously achieve reasonably favorable properties. So reasonably low switching current and reasonably high TMR ratio and reasonably high thermal stability factor or retention properties with the thickness of the cobalt iron boron of the 1.7 nanometers. And for the probabilistic computing applications, you need to enhance the hopping between these two states. And this can be easily achieved by just reducing the height of the energy barriers between the two states. And this is possible by just increasing the thickness of the cobalt iron boron from 1.7 to around 1.9 nanometers in our experiment. So as shown in this figure, so this figure shows the retention time of each state as a function of the thickness of the cobalt iron borons for 4 different diameters of the MTJs. So as you can see, the retention time is reduced from 10 years to around millisecond time scales. And if we observe in the time domain, we found that the state of the magnetization or the resistance of output resistance fluctuates in time with the millisecond time scales. So that this result shows that our device has controllable stochastics, so which is the fundamental requirement to construct the probabilistic bit. So next we constructed the probabilistic bit or p-bit using the stochastic magnetic tunnel junctions. So this shows the unit circuit of the probabilistic bit, which consists of one magnetic tunnel junctions and NMOS transistor resistance and resistor and comparators. And this shows the obtained or measured time averaged output voltage as a function of the analog input voltage. And these three panels shows the time domain signal, time domain output voltage as a function of the time for different input voltage, 1.875 to 2 volt. So as you can see, at the input voltage of 1.95, we see an equal fluctuation, the fluctuation with the equal probability between 0 and 1, and the balance can be changed by just changing the input voltages. And this shows the time averaged output voltage, which can be well fitted by the sigmoidal function. So this results means that our probabilistic bit can be used as a binary stochastic neurons, which is the fundamental unit of the probabilistic computing or the stochastic neural networks. Okay, so next we constructed a probabilistic circuit consisting of 8 probabilistic bit from p-bit 1 to p-bit 8. And these p-bits are connected with the synaptic weight logics, which is we used Arduino microcontrollers. So we have 8 stochastic MTJs here, and NMOS transistors and resistors. So the each p-bit fluctuates in time, and depending on the state at each time, the synaptic weight logic calculates the next input that can lower the total energy of the probabilistic bit. Okay, So next, I will explain the cost function or the algorithm for the integer factorizations. So this is the cost function or energy to solve the integer factorizations. So the large F is the numbers we would like to factorize, and the large X and large Y are the numbers we would like to find. So these are the factors we would like to find. So as you can easily understood, if the large X, large Y, so X by Y becomes F, the lowest energy can be obtained. So so with this cost functions, we can solve the integer factorizations. And large X and large Y can be represented by this binary forms, and small y, x1, x2, x3, y1, y2, y3s can be represented by each p-bit. Okay, so let me take an example to factorize 35 by 4 p-bits, for examples. Okay, so if we substitute 35 here and we use 4 p-bits, so 1 plus 2x1 plus 4x2, 1 plus 2y1 plus 4y2, and we substitute this large X and large Y to here, the energy can be represented as shown here. So here the coefficients are rounded off to have one significant digit. So this is the energies to solve the integer factorization of the 35. And here there's one important point. So we have 3-body interactions and 4-body interactions here. And this kind of the multiple interactions, multi-body interactions is not easy for the quantum computers to solve. But for the probabilistic computers, it is easy because we can interact between each p-bit electrically. Okay, and for the input to lower these energies, the input to x1, x2, y1, and y2 bits can be calculated by the derivative of the energies with the state of each p-bit, as shown here. So what we need to do is just programming these interactions to the synaptic weight logic, and then the system can automatically calculate the integer factorizations with this algorithm. Okay, so let me show the experimental results. So first we tried to factorize 35 using 4 p-bits. So this shows the histogram before we turning on the correlations. So at this stage, we observed each state from 1 by 1 to 7 by 7 with the almost equal probabilities. But once we turned on the interactions or the correlations, we observed higher peaks for the 5 by 7 and 7 by 5, which is exactly the factors of the 35s. And we also performed the same experiment for 161 and 945 using 6 and 8 p-bits, and we observed a higher peak at the correct answers of the integer factorizations. So these results means that our rudimentary probabilistic computers can solve the integer factorizations using the algorithm of the optimization problems. Okay, so at the last of these sections, I would like to briefly comment on the comparison with the competing technologies. So first, I'd like to discuss the comparison with the quantum annealing machines. So the quantum annealing machine, or the D-Wave, can also perform the optimization problem, executes the optimization problems. But compared with the D-Wave or quantum annealing machine, our probabilistic computer based on the Spintronics can be operated at room temperatures, and so manufacturable at the megabit to gigabit level, because our magnetic tunnel junction is based on the current STT-MRAM technologies. And also the probabilistic computer with Spintronics can implement various correlations, including many-body interactions easily, because the p-bits can be interacted electrically. Okay, and next I'd like to discuss the comparison with the CMOS-based probabilistic computing. So as the previous speaker mentioned, the CMOS circuit can also generate a skewed random numbers, but because the CMOS is a deterministic element, if you want to have random numbers with a certain length, you need to have a large number of the transistors, which requires a large footprint and also the energies. And from our estimations, our MTJ-based pivot can realize the energy with 10 times lower, and also the pivot can use just about 300 times smaller transistors is required. So this means that the probabilistic computer with Spintronics can achieve a much smaller energy and area than the CMOS-based probabilistic computers. Okay, so with that, let me move on to the next part and discuss the device technologies. And I think I have more 10 minutes, or so I can.
Yeah,
Okay,
10
so
minutes we have.
10 minutes. Okay, so. In the previous part, I showed a demonstration of the integer factorization using perpendicular easy access cobalt iron boron based magnetic tunnel junctions. And with this MTJs, the fluctuation of the magnetization or the fluctuation of the resistance is around the millisecond time scales. And we use 8 pivot. And if we scale up the computers, we need to make the fluctuation faster for large scale problems. And for that, how we can achieve it. And we know that the retention time or the relaxation time can be given by this Arrhenius law. So I guess that you will easily, your answer is that by reducing the thermal stability factor E over KBT or delta, we can achieve a shorter tau. And we also thought that, but we found that this is not complete. So I will show the reason why this is incomplete. So this shows the numerical calculation based on the Landau-Lifshitz-Gilbert equations. So we first calculated the perpendicular easy axis MTJs and in-plane easy axis MTJs. And the thermal stability factor delta, E over KBT, is 3.8 and 3.8 for both cases. And for this perpendicular MTJs, the magnetic anisotropy field of the perpendicular MTJ is 10 milliteslas, and the anisotropy field along the in-plane direction is also 10 milliteslas, and this negative minus 10 millitesla perpendicular anisotropy means that you need to apply a 10 millitesla along the perpendicular direction to change the magnetization of the magnetization direction from the x-axis to the z-axis. Okay, so these two are equivalent with each other. So the fluctuation time scales are almost the same as we expected. And next, so the point is that the thermal stability factor is the same. And next, we just changed the anisotropy field along the perpendicular directions. So for this case, the easy axis anisotropy is 10 millitesla. So the thermal stability factor or the height of the energy barrier is the same, 3.8, but the fluctuation time scale are largely different. So the point is that in the in-plane easy axis MTJs, the tau, the fluctuation time scale or the retention time strongly depends on the perpendicular negative anisotropy field, HK effective, although the delta is independent of the HK effective. Okay, so as I mentioned, the Neil-Arrhenius law is tau equal tau zero exponential delta. So we should attribute the difference between these threes to the difference in the tau zero. So we can anticipate that the tau zero depends on the HK effective. So from the obtained fluctuation time scales, we calculated the tau zero as a function of the perpendicular anisotropy field, as shown here. So we found that for the uniaxial magnet, the tau zero is somewhere around 20 nanosecond, but by just increasing the perpendicular easy axis anisotropy field, the tau zero gradually decreases to down to less than 1 nanosecond. So the point is that the tau zero changes by 2 orders of magnitude with the HK effective perpendicular anisotropies, and the tau zero in the in-plane MTJs are always shorter than that with the P perpendicular easy axis MTJs. So this is the case of the perpendicular easy axis MTJs. So, okay. And the making the long story short, the physics governing the tau zero can be understood as follows. So this shows that this is the Neil-Arrhenius laws, and the tau zero is given by these equations. So for the perpendicular easy axis MTJs, if you decrease the perpendicular easy axis anisotropies, so perpendicular anisotropy field, you can decrease the thermal stability factor, but your tau zero, the time constant of the fluctuation increases because the tau zero is inversely proportional to the gradient of your energy landscapes. And for the in-plane easy axis MTJs, if you decrease the in-plane anisotropy field and increase the perpendicular anisotropy field, you can decrease the thermal stability factor E over KBT, and also you can decrease the tau zero. With which, that's why we could obtain the shorter tau by in the in-plane easy axis MTJs. So with this guideline, we fabricated stochastic MTJs using the in-plane easy axis materials. So this shows the stack structure we used, and this is the SEM image of the fabricated device. And so we the perpendicular anisotropy field is set to around minus 0.5 teslas. And this shows the DC resistance as a function of the in-plane easy axis in-plane magnetic field. So we observe a zero coercive field, which means that our device shows the stochastic behavior, and our device has a super paramagnetic properties. And we measured the random telegraph noise using this circuit. So we found a very fast random telegraph noise, so with the time scale of nanosecond. And so this shows the relaxation time of the parallel and anti-parallel state as a function of the in-plane field. So we obtained 8 nanosecond fluctuations for the device B. And if we plot these results to the history of the relaxation time of the stochastic MTJs, we found that our device can achieve a 100 times shorter fluctuation time than the previous records. Okay, so that's all of my presentation. So let me summarize briefly my presentations. So so at the beginning of my talk, I described that the probabilistic computing is very promising for computationally hard problems without utilizing the quantum mechanics. And I showed a proof of concept demonstration of the integer factorization using stochastic magnetic tunnel junction devices. And after that, I described a nanosecond stochastic magnetic tunnel junctions, and we've clarified the mechanism governing the different time scales of the relaxation time between in and perpendicular MTJs. And the point is that the in-plane MTJ is preferable because the tau zero and delta, or the thermal stability factor E over KBT, can be controlled independently. And we achieved a nanosecond random telegraph noise down to 8 nanoseconds at negligible bias. Okay, so that's all. Thank you for your attention.
Thanks, Prof. Fugami. Now the talk is open for questions. Does anyone have questions?
Professor Fukami, it was a very interesting talk. I have a question on the HK in your devices, the last devices you
Okay.
said. You are increasing the HK by increasing the MS of the layer. Are
Okay.
you-
So how we increase the HK
particular-
effective?
Yeah, yeah.
Okay. So we just tune the thickness of the cobalt ion boron.
Okay, so
So by increasing the thickness of the cobalt ion boron, the in-plane anisotropy becomes so the it becomes difficult to turn the magnetization from in-plane to perpendicular, which means that the negative perpendicular anisotropy becomes larger.
okay, thank you.
Okay.
Any questions?
May I ask a question?
Okay.
Yeah.
It was a very nice talk. Thank you. So, Prof, I have a question. In random telegraph noise, the results that you have showed. So you said that the in-plane MTJ is preferred, but for the on-chip devices, maybe perpendicular MTJ is more preferred because of the density of the devices. I mean,
I think no, because the for the MRAM applications, perpendicular MTJ is preferable because we need to ensure the thermal stability factor. But for the stochastic applications, so the probabilistic computing applications, you do not have to care about the retention.
yeah, right.
You can reduce the size freely. Okay.
Yeah, but I mean, there should be some certain spacing between two MTJ cells because there will be some magnetostatic interaction. There could be some magnetostatic interaction.
I see. Okay. But that's also the case for the perpendicular MTJs. I roughly understand your point, but the if you want to pack the MTJ very densely, that will become the problems, I think. But the in reality, if we can realize, for example, 1 megabit probabilistic computer, that's already very, very useful.
Yeah, okay.
Because the D wave is kilobit. Okay. And to realize megabit probabilistic computer, we do not need to pack the MTJ such so densely.
Okay, yeah. Thank you.
Yeah, hello.
So Fukami, I have one question related to the speed of the operation. So like for this particular, like you move from out of plane to in plane material system.
Yes.
So in this case, because perpendicular magnetic anisotropy, if you have the operation would be faster, I mean to say, but when you switch to in plane magnetic anisotropy, how would be the operation speed?
Sorry, so could you repeat your question? I couldn't hear well.
The speed of the operation. In terms of the speed of operation, how can you define it? Yeah, if you are taking in plane material.
Yes, so that's the point. So the by increasing the fluctuation speed, we can shorten the calculation time. So the calculation time is directly dependent on the fluctuation time scale.
So you mean like from the Arrhenius equation, the tau, you mean to say tau?
Yes. The shorter tau can give you a shorter calculation time.
Okay, understand. Tenli, yeah, you can ask a question.
Yeah. Oh, yeah, thank you. Thank you. Prof. Thank you very much. So I want to ask, can you explain how do you use coupling waveguide to measure your device?
So
coupling waveguide. Yeah, coupling waveguide. So your slides shows you use the coupling waveguide.
I couldn't hear well, so coupling with what?
Coupling waveguide. So just now your slides shows your
Which page?
Coplanar waveguide.
Coplanar waveguide. Okay, okay. So and so we use the coplanar waveguide.
I mean, how do you use this to measure the device?
The this is the measurement circuit. Okay. And
Yeah.
this device has a coplanar waveguide.
Oh, you
Yes,
mean
we have it.
you put your device on the coupling waveguide?
No. So the
No?
device is connected to the coplanar waveguide.
Device. Okay.
So we have a probe here, and the probe is attached to the pad. Sorry. So okay. And the pad is connected to the coplanar waveguide. And in between, we have one magnetic tunnel junction. Okay. Do you understand? Okay.
Thank you.
Okay.
Yeah, we are on time. So yeah, then no questions. So we can close this talk. Yeah.
Okay. Thank you.
Yeah. So we have 10 minutes break here. So you can keep it on Zoom and you can come back after 10 minutes.
Okay, thank you.
Yeah, thank you.
Mukesh, we can try to share your slide first.
Okay. Welcome back. Our next speaker is Dr. Durgesh Kumar from NTU Singapore. He will talk about novel engineering of spin-orbital layout for energy efficient synaptic devices. Yeah, you can go on, Durgesh.
Thank you. Can you see my screen?
Yes.
Okay. Good afternoon, everyone. My name is Durgesh, and today I'll be talking about novel engineering of spin-orbit torque layer for energy-efficient synaptic devices. So as we know that artificial intelligence is being accepted in variety of applications such as portable devices, self-driving cars, and many more. However, these intelligent tasks have been achieved using intelligent algorithms in existing von Neumann architecture, where huge amount of data travels back and forth from CPU to memory unit, and also consumes a huge amount of power. Therefore, there is a need to come up with an energy efficient architecture. And one such energy efficient architecture is brain inspired computing or neuromorphic computing, which is a complex network of numerous neurons and synapses as shown here, where neurons act as processors and synapses forms the bridge between pre-neurons and post-neurons. Moreover, they act as the memory unit. At present, several materials are being studied to realize the neuromorphic architecture. And out of these, domain wall devices are one of the most energy efficient contenders. One thing to note here is that these domain wall devices are driven by spin transfer torque. This power can further be reduced if we utilize spin orbit torque in place of spin transfer torque. But the question comes that can we reduce the power further? And one of the knobs that we can tune to get further energy efficiency is the spin Hall angle, which is the quantification of charge to spin current conversion. And if you look at the conventional heavy metal materials that are being studied to get high spin Hall angle, tungsten gives rise to maximum spin Hall angle. However, this spin Hall angle is being achieved in beta phase of the tungsten, which is being deposited at low power and high argon gas pressure. That gives rise to this kind of granular structure and results in the problems of high resistivity, more defects, and hence larger energy consumption and lower tunnel magnetoresistance, which are the problems at the first place. So we have proposed a new design to overcome these problems, where we have sandwiched a low pressure deposited tungsten layer between magnetic cobalt iron boron layer and high pressure deposited tungsten layer. So by doing that, we anticipate into fewer defects in ferromagnetic layer that may result in low critical current and hence low energy consumption, higher tunnel magnetoresistance, and optimized spin Hall angle or even higher spin Hall angle. So to investigate this in detail, we have studied these 5 different samples where we studied single spin Hall layers made up of low pressure 6 nanometer and high pressure 6 nanometer layers for reference samples, and dual spin Hall layers with the combination of high pressure and low pressure deposited films with different thickness combinations. Firstly, we characterize the thin films and we perform the hysteresis measurements of our samples, and we observed perpendicular magnetic anisotropy in our films in as deposited state, which is a hint of beta phase in tungsten. When we plotted coercivity as a function of high pressure deposited tungsten thickness, it increases as the thickness of high pressure tungsten increases. Moreover, the coercivity remains at quite low values. Further, we measured the surface roughness of these samples, and it takes a similar relation to that of coercivity, which is attributed to the fact that high pressure deposition gives rise to granularity, and that this granularity increases as the thickness of high pressure tungsten increases. Further, we electrically characterized our films and measured the stack resistivity of our films, and we found that high pressure 3 nanometer, low pressure 3 nanometer, which is also abbreviated as sample D2, has stack resistivity more than 120 microohm centimeter, which indicates that this is in beta phase. So we made domain wall devices from this HP3 LP3 sample, and also from low pressure 6 nanometer and high pressure 6 nanometer samples to compare our results of dual tungsten with these reference samples. And then we moved on to the central portion of our study, where we measured the current driven domain wall motion. For that, we applied the pulsed current as shown here, and observed the domain wall dynamics using the Kerr microscopy. First, we measured the samples with high pressure 6 nanometer tungsten layer, and we could not see a controlled domain wall motion in those devices. However, when we moved on to our dual layer samples, we saw that domain wall moves from one end to the other end in a very systematic manner. Moreover, the domain wall motion can be achieved at low currents of 10 to the power 7 ampere per square meter. Further, we studied this aspect in detail and varied the out of plane magnetic field and applied current density to various values, and in both the directions, positive as well as negative. And we observed that we could move the domain wall to the current densities as low as 10 to the power 6 ampere per square meter. However, in LP6 and HP6 devices, we could not see a controlled domain wall motion. So such low current densities that we observed in our samples that translate to an energy of the order of femtojoules, which is much lower than the one in the literature. Further, we tried to understand the reasons for such low current density observations, and we measured the spin Hall angle and using harmonic measurements, and we found that the spin Hall angle of dual samples is not much different. So we anticipated that our samples must have a very low pinning field, and for that we studied the domain wall dynamics as a function of out of plane magnetic field, and we could see that in dual layer samples the domain wall can be moved at very low out of plane magnetic field, and we plotted velocity as a function of out of plane magnetic field, and we found that the pinning field in our dual samples is 2 millitesla, which is quite close to low pressure deposited 6 nanometer samples. We also measured the pinning site density in our samples, and we found that LP dual layer samples have intermediate values to that in low pressure 6 nanometer and high pressure 6 nanometer devices. Owing to such low current density and hence energy consumption in our devices, we also studied them as a synaptic devices. But before, I would like to briefly introduce how the domain wall device-based synapses look like. So as we know, in magnetic tunnel junctions, junction devices, we can get 0 and 1 state depending on the magnetization configuration, either in parallel or anti-parallel direction. However, in domain wall magnetic tunnel junction devices, we can stop the domain wall at intermediate positions, and hence we can get intermediate resistances compared to the lowest resistance state and highest resistance state. But a domain wall motion is stochastic in nature, and it is very difficult to control the specific position. Therefore, we propose the concept of meander wire, where two segments of the domain wall meet at a certain offset of d, as shown here. However, moreover, this offset increases by 5% when we go from the first pinning side to the second pinning side from the left, and so on. So we studied the domain wall dynamics for different d values, and we observed that for d equals to 50% and above, systematic domain wall pinning and depinning was observed at all 4 pinning sites. However, for low D values, domain wall pinning was not observed. So from these, we could say that these devices can potentially be used as stochastic as well as deterministic synapses. With that, I reach to the summary of my presentation, where we have proposed and studied the dual layer devices, and we demonstrated very low current densities, which translate into the power of femtojoule, of the order of femtojoule. And this is mainly attributed to ultra low pinning field of our devices. We have also shown stochastic and deterministic synaptic devices from our domain wall devices. Finally, I would like to thank NRF CRP grant and A-STAR AME grant to support our work. Thank you so much for your attention.
Thank you, Durgesh, for your talk. So now the talk is open for questions. Okay, I have a question regarding this domain wall devices. So like I see this domain wall pinning, and you can clearly see the step resistant states. So did you try to see what are the domain wall velocity in these devices?
Domain wall velocity is around.
I mean, does it impact on the tungsten method that you proposed?
Domain wall velocity is around 1 meter per second, but in this study, I mean, at the moment we focus more on the power reduction aspect rather than the domain wall velocity.
So I mean, did you try to make any single nanowire which is smooth nanowire, straight single nanowire, where the domain wall was driven and velocity was measured?
Yeah.
Kind of study.
Yeah, we have done. I mean, one of the studies, one of the wires, I mean, the set of wires is this. In this case, you can see some edge effects, but later we also made some other devices, and we measured. I mean, we tried to look for the edge effect and everything.
Any questions? If not, then we can move to the next talk.
Thank you.
Yeah, thank you, Durgesh. So our next speaker is Sonal Shreya from Aarhus University, Denmark. She will talk about modeling of spintonic devices for application-based circuit level integration. Hi, Sonal. Yeah, you can start.
Hello, everyone. So am I audible?
Yes, yes, you.
Okay.
You can share your presentation.
Share my screen. Is it perfect?
Yeah, it is visible. Yes.
Okay. Okay. Hello, everyone from all around the globe. And I'm Sonal Shreya from Aarhus University. And at first, I would like to thank the committee and organizing members of BICPAMA seminar. So my talk today is based on the perspective of modeling that can be used for various applications of and circuit level and maybe on system level integration. So at first, I would like to discuss some of the modeling perspective, that why we need modeling and how we do the modeling. So as you can, let me start the pointer. So as you can know that device modeling is not something new. It has been carried out since we have using all the CMOS devices, NMOS, PMOS, and their modeling is very mature that we see in terms of BSIM model or PTM model. So all those models are so mature just because they has a close proximity with the foundry, and they know all the requirements and specifications of the foundry. So those got with time got so matured. So but what about the novel devices? Because nowadays, since past 1 decade or 2 decade, there are so many new devices that has been proposed and researched. So in order to incorporate those models with the existing devices, we need some model that can be used for circuit simulation. So for that, we usually go for hardware descriptive language, where we write a code in Verilog A. So Verilog A is for analog, that is electrical module of the model. So the physics-based modeling we used to do, where we use some of the macro spin approximation. For example, we know that in magnetic devices we use LLGS or Thiele equations, but the model need to be accurate. But the advantage is that it is technology independent. That means we can modify it according to, if suppose if we want some, we know some foundry or some manufacturer that can manufacture our device, then according to their specification and their requirement, we can modify the model accordingly. The model that we will develop need to be accurate and computationally efficient. Then once the model is ready, then we can use it simply by using any of the SPICE platforms, such as HSPICE or Cadence for circuit level simulation. And as we already know that if we have the model and we do the circuit designing and then layout, obviously if we are doing the analytical model, then we do not have the layout for the device, but with time and with maturity it can be done. So we do all these things, simulations and its variability analysis and so many things, just to avoid the failure before fabrication, because we know that if an IC is fabricated and it's faulty, then there is no going back. For how can we increase the accuracy, we need to use less approximation, and we can incorporate the thermal and temperature dependency, thermal fluctuations and all these things, so that we can avoid the normal problems that the model can have. So an overview of this, that what device to system level is this, that first we need to do the device modeling in a Verilog A code, then we do the device characteristic. But then this device characteristic need to be on both ways. That is, we do the micromagnetic simulation or with characterization of the sample, or then on the Cadence or HSPICE platform, we do the characterization of the model, and then we do the validation by matching both of these. And then once the model is designed, then we go for the bit cell level circuit designing. So first we have the design device, and then we do the bit cell of that device, and then do the characterization, and then go ahead with the application of application based circuit design. And if we want to do, for suppose if we want to do a memory bank or memory, then we need to go for we need to have the peripherals, we need to get its latency, area, and so many characteristics. So then we can use a few like NVSIM or those kind of simulators. And then on system level, that means we want to design a neuromorphic computing system or neural network, and we want a system level performance analysis. Then either we do the SOC design and then fabricate and test it, and then on simulator level we can do we can use NeuroSim, Brian, and all those simulators. So this is an overview of a prototype, maybe we can call, of the device modeling, that how for a spin device we can do the modeling. So at first you can see here that suppose this is a 2-terminal black box of the device. So first we put all the geometrical parameters and device parameters, and we set the range of all the parameters that so that we can modify accordingly. And then we need to find out that which kind of magnetic dynamics will be leading this spin device. Either it is LLGS for magnetic switching, or it is a Thiele equation to find the position and velocity of skyrmion or vortex, such kind of devices. And then we find out the output in terms of magnetization switching, or the position and frequency. But then we also have to relate each of the physics and analytical model of the device, so that we can transform it in form of electrical signals. So the output will also be having in form of current and voltage. So some of the related research work that I have carried out in past few years are that the modeling of VCSOT spin device, that is voltage controlled spin orbit torque. So as I said, that first we need to know the phenomena of the device. So as it is 3-terminal device, then this is following the VCMA mechanism, that is voltage control magnetic anisotropy. So according to VCMA mechanism, how the barrier lowering is happening, and then what kind of switching it will take, how much time it will take, then accordingly we need to modify the LLGS equation. Then we need to have its equivalent resistance circuit, because as I said, that we need to have the electrical module of the device, and inside this all the analytical model and all the equations, that is for example equation of effective magnetic field, all these will be followed. And once the model is designed, then we go for the bit cell design. So for example, this is a 3-terminal device, so we need a read transistor and write transistor, and as in VCMA, the read transistor also works as write transistor. So this is the bit cell circuit of circuit design of the VCSOT device. And then we can do the transient analysis, DC analysis, and so many other analysis that is available on Spectre or HSpice simulators. So I have also proposed a multi-level that, or for example, multi-bit VCSOT device where we can store 2 bits simultaneously. So this is a parallel structure and this is the series structure. So in this, again, first we need to know that how the resistance, equivalent resistance circuit will look like, and then we do some calculations, modify the model, and then we do the basic bit cell designing of those devices. And these are the optimized parameter for 2-bit, that how much should be the free layer length, the RA, the thermal stability factor, and all those things. And then once our device is designed, then we move ahead with the circuit designing. So we can start with obviously with the smallest thing, that is the logic gates. So for that we need to define the resistance equations accordingly. So here, like for example, R1, R2 can be the parallel and anti-parallel resistance of the device, and suppose R3 is the resistance of the heavy metal. So how the path of read and write will be followed. So all these things will be done. And why we need a computing in memory, as we already know that for computing in memory, it provides us a saving of time and energy. That's why we go ahead with the computing in memory designs. So in this, for example, this input or column is taken as a read, and this is as a write for logic devices. And now, suppose we want to do the neural network. So for neural network, what are the main requirements? First is synapse, and second is neuron. So we want to design our memory device in terms of a synapse, so that this can work. This can be used as a synaptic device, and then this is a neuron, and then we encode this for the requirement. For example, in BNN, we require the smallest module as XNOR. So we encode these bits in terms of XNOR operation, and then we see that how the neuron output is will look like, that whether it is activating or deactivating, how it is performing. And then for the bigger neural network level designing, first we need to think and see that how we can design the synaptic crossbar array and how it will behave, how the current bitline current will be followed, and how it will be added, so that because we know that in neural network the output neuron depends on the weights and the total input. So the input will be current here, and the weights will be the conductance of each of the magnetic devices, and then all these will be added here, and then decides that whether the neuron will be activated or not. So this is the circuit that I proposed during my PhD work, where these each of the synaptic device is capable of storing 2 bits. So this will be then like each of these are saving 2 bits each. So 8-bit synaptic array, and then 2 of the neurons. So if I would like to summarize the whole whole thing and whole concept, then it is like that device modeling is the pathway for the novel devices that can be taken towards the IC designing. Then we need to know the dynamics of the device and the analytical physics behind the device so that we can do the device modeling. Then I discuss some of the my proposed work, that is the MV multi-level VCSOT voltage controlled magnetic anisotropy SOT based device, and how it can be used for CIM and BNN applications and so on. And then how with the device model we can go ahead with the circuit and system level design. So as we already know that the future of Spintronic is very bright, and now as it has capability to involve itself or relate itself with other domains such as magnonics and optics, which leads us to so many different devices, for example, spin oscillators, vortex, fermion, and photonic control devices, spin quantum, and these all devices need to be modeled so that we can look for a bigger picture, that is application level designing, because from application level design we can design any artificial intelligence system, then neuromorphic computing system, biomedical, neurotechnology, and there are so many IoT applications and so on. So the takeaway from my talk is that I will motivate all the researchers in Spintronic field to look towards this device modeling side of the device where we are lagging a little, and go ahead with the applications of the Spintronic. So this is the small Spintronic group in my university, and thank you so much for your patience listening.
Thank you, Sonal. Yeah, thanks for nice presentation. Now the talk is open for questions.
Sonal, I have a question. What is the most challenging aspect of device modeling?
So I would say that most challenging aspect is to understand, because being an electrical engineer, it becomes sometimes very difficult to understand the physics of the device, because without understanding the actual physics and how the analytical modeling can be done, because sometimes we find it in the literature, but sometimes we need to do the calculations and simplify it so that it can easily be incorporated in the model.
Okay. What is your important contribution in some of that?
My important contribution is to develop the model, and as I am again going ahead with the modeling of the devices, for example, currently I'm focusing on the modeling of oscillators. So understanding the analytics of the device and relating it with the physics, and making a bridge between the analytical physics of the device and the electrical module, so that it can be linked and come out as a electrical module of the device.
Okay, my question is like this. So before you joined the group, right, your PhD group, your seniors would have done something. So what is that thing that you contributed to the lab?
Oh, yeah, so my seniors also started working on the modeling. So then I get motivation from there. They did some modeling for a two terminal STT device. Then I thought that how we can go beyond that, if we want to design the 3 terminal model, and then we want to design the 2 multi-bit. So for 2-bit, then I thought of the the device structures, that the geometry that can be capable of storing 2-bit instead of 1-bit. And then I passed on this in my PhD group, that now they are focusing on some other devices, for example, domain wall and fermion. So this is a chain that is going on.
Okay, thank you.
Thank you.
Question. Sonal, I have one question. Anand is here.
Yes.
Yeah. You spoke about in-memory computing, right?
Yes.
And you also spoke about spin quantum, which is a as what we can say emerging area in Spintronics, right?
Yes, yes.
And you also spoken about neuromorphic computing.
Yes.
Basically, neuromorphic computing has the ability of adaptability through the synaptic weights adjustment.
Exactly.
Right. Now, whatever you explained or whatever you presented, that was on the
Yes.
classical platform of the neuromorphic computing.
Yes, totally
Right.
agree.
Now there is one more platform. Basically, when we talk about classical computing, it is a
Yes.
sequential and it is not that much faster as compared to the quantum computing.
Yes.
Now, quantum computing has the inherent ability of parallel processing, and it has the faster speed as compared to the classical computing. Now, my
Yes.
question is, can we see in near future realization of neurons on a quantum platform or on a qubit with the help of the qubit architectures?
Yes, thank you for your question, sir. So yes, it is a very challenging task because now so many groups are moving towards and working towards the quantum computing, not only in Spintronic but in other device areas as well. So of course, I think that it is possible, and in near future, maybe in 5 years or so, we will be able to see such progress in these quantum field.
Thank you.
We'll just
Thank
take
you.
last one question from Prof. Tanaka.
Yes.
Yes, a simple question. Could you tell us about the policy of verification of your model? How do you do this?
Yeah, so there is 2 ways by far I have done it. So either we take likewise I did usually in my PhD work, because there we had some lack of collaboration with the manufacturing groups. So we take the literature-based experimental results, and then we verify the model characteristic, for example, the RV characteristic of the device, or that how the read current and write current will be characterized. Or the second thing is that we have the fabricated sample, and then we do the characterization of the device in the lab, and then the model output need to be validated from that. So here in my when I'm working as postdoc at Aarhus University, so we have collaboration with many manufacturing R&D sectors like Spintech, INL. So we can get samples for the device from them, and then we do characterization and then validate.
Okay, thank you very much.
Thank you.
Yeah, thank you, Sonal. With this, we are closing this talk. So
yeah,
I will hand over to Prof. Prem. So if he
thank
wants
you
to
so
say
much.
something.
So I will stop sharing.
Yes.
Okay.
Okay, thank you everyone for attending today's sessions. So we'll meet again tomorrow. Maybe I'll pass on the podium to Professor Tanaka.
Okay, see you tomorrow.
Yeah, see you all tomorrow. Bye.
Thank you. Bye.